Hi, everyone out there in the ether. My name is Melissa Zhang, and I want to first thank Micah, Sujoy, and Rob for inviting me to give this asynchronous seminar talk with the glorious acronym that is so clever. I work with classical knots and definitely with the algebraic invariants related to them. So that's why this is in red. Okay, so today I will talk to you about this forthcoming work. The paper should be out soon with Ross Akhmachet, who is a grad student of Slava Krishkal at the University of Virginia. We're both on the job market, so I just want to advertise that Ross is a great mathematician and you should totally hire him. Okay, so what our work is about is we were inspired by all the algebraic constructions that can be extracted from a certain version of knot-Floer homology. So knot-Floer homology is related to Heegaard-Floer homology. You actually just look at the knot embedded inside, let's say S3, and the knot complement is determines the knot in S3. So you sort of look at the Heegaard-Floer homology of the knot complement, and that is knot-Floer homology. In particular, the algebraic structure involved allows us to create a one-parameter family of filtrations on this chain complex, and Oshpad-Lipschitz-Szabo defined this numerical invariant called upsilon, such that for every number t inside 0 to 2, you get a number that turns out to be a concordance invariant. It's actually a concordance homomorphism. So what we did was we looked at this new version of Khovanov homology. You can think of it as an extension of standard Khovanov homology. In essence, we are going to basically have a Frobenius algebra such that the roots of a certain quadratic are actually in our ground ring. So we have a lot of coefficients. And it turns out that the algebraic structure of this version of Khovanov homology, introduced by Khovanov and Robert in 2018, is going to be somewhat similar to knot-Floer homology. So in our paper, we tried to explore how we can make the algebraic structures look more and more similar, and therefore what can we extract out of this complex. Okay, so let me first start with a warm-up, which is going to inform the way that I want to think about Khovanov homology throughout this talk. So if I think about the simplest version of Khovanov homology, well, first of all, for me, I don't want to work with signs. So I'll just let R be the ground ring. And let's say that the ground ring is just F2. Now from this ground ring, we are going to need a Frobenius algebra. And I'm going to call this curly A. And it's given by, you take your ground ring F2, take the polynomial ring, and you mod out by x squared. So what this does for me is that it tells me, well, first of all, it's an algebra, so it has a multiplication inside it. It has this ring structure. Okay, so let's just look at this and describe what the multiplication map should look like. You're supposed to take 2 copies of your algebra, and this is tensored over your ground ring F, and you multiply them together. I like to draw the generators of A tensor A as an F2 vector space, because this is how the Khovanov homology of a knot is actually defined. So over here on the left, we have 4 dimensions over F2, and they're going to be generated by, well, if you look at the Frobenius algebra, as an F2 vector space, it's generated by 1 and x. So if 1 tensor 1, x tensor 1, 1 tensor x, and x tensor x here. And then on the right, I just have 1 copy of the algebra. if you multiply 1 times 1, you get here. X times 1 and 1 times x are the same thing. So this is a commutative Frobenius algebra. And x times x is 0. Similarly, the reason why I'm saying this word Frobenius is because it actually has a co-multiplication structure as well. So this is a dual concept of multiplication. We take one thing and we can split it into 2 copies of the algebra. And again, I'm going to think about these as F2 vector spaces. And I'm going to write down the basis elements. And the way that you should think about how co-multiplication is defined, at least for the purpose of this talk, is that it's really dual to the multiplication map. So what that ends up meaning is that you can just take this picture and flip it 180 degrees around, and you will end up with a map like this. Okay, so the interesting thing about Kavanagh homology, it really comes from the fact that for every commutative Frobenius algebra, it's related by bijection to a 1 plus 1 dimensional TQFT. And TQFT stands for topological quantum field theory. It basically just means that you can assign to each closed one manifold, which is a circle or a bunch of circles, you assign the algebraic analog to it, which is this algebra here. And then for cobordisms, you get to assign maps between them. So for instance, if I look at this linear map between F2 vector spaces, or you can think of it as maps between this module and this module, you see that this is really representing 2 circles becoming 1 circle. So I can really think of this multiplication map as a merge map of 2 circles merging into 1 circle. So that's just a pair of pants cobordism. The dual picture is just the dual drawing in the TQFT. So it's the pair of pants the other way. Okay, so what we're going to do throughout the talk later is we're going to modify the Frobenius algebra that we're working with, which basically means that the multiplication and co-multiplication maps are going to get modified a bit, and then we'll see what happens. Okay. So next, I want to set some notation and also describe a little bit more explicitly how Kavanagh homology is defined, because I haven't actually told you what Kavanagh homology is. I just told you its building blocks. So here's my notation. If I ever write K, that's going to be a knot in S3. And in some cases, I might want to think about a link L, and I'll tell you when I do. But in general, the purpose of this talk is to study knots. If I ever write D, that's probably going to be a diagram associated to a particular knot. So this is a diagram that represents K. So this is a diagram either on R2 or S2. CKH of D is going to be the Kavanagh chain complex. So the beautiful thing about the Kavanagh chain complex is that you can actually basically teach anyone to write it down. So for example, I'm going to use the hop link as my quote unquote knot, it's actually a link, because it has very few crossings, and this is a small enough example. So let's say our diagram for my hop link looks like this. Okay, this diagram has two crossings, and what I'm going to do is think about smoothing out these two crossings so I get totally planar circles so that I can associate the algebra to each circle. So for each crossing, it's going to look like this. I can smooth it in two different ways. This way is called the zero smoothing, and this way is called the one smoothing. It's just a controlled way for us to write down how the slight overpass that we have can be just smushed directly down onto an actual embedding in the plane. So now I think about my two crossings, and each of them can be smoothed in two different ways. So combinatorially speaking, I have 4 different complete smoothings of my picture. And I order them according to basically the poset that you get from comparing the binary strings. So if I smooth this 0, 0, that string is less than 1, 0. And I'll order them in a binary cube as follows. Okay, so if I do 0, 0, I get a picture that looks like this. 2 little cashews. Okay, then I get this up here, this down here. And then if I smooth both of them with a 1 smoothing, I actually get this picture. And here are the arrows representing the poset relation. So now that I know I have a TQFT, well, I can assign vector spaces to each of the vertices of my cube. So this is going to be assigned A tensor A because there are 2 circles, whereas this is assigned A. And also there's a cobordism between these two, and it's a local cobordism that changes this 0 smoothing to a 1 smoothing here, but keeps this the same. So I can think of that as a saddle. Namely, it's going to be the merging of 2 circles because I know my map has to go from 2 copies of A to 1 copy of A. So once I've done this transformation from pictures into vector spaces and linear maps, I actually have a chain complex. Now you might be asking, where's the homological grading? And that's very simple. It's already drawn. It basically depends on the weight of your binary string. So horizontally, I have my homological gradings, and it's actually cohomological theory. So as I go to the right, as my differential progresses, I increase in homological grading. Once we look at this extremely carefully, you'll actually note that each of these faces of your binary cube, which might be any dimension, they actually commute. So since we're working over F2, that means that we have a chain complex such that d squared is just 2 copies of the same map, and therefore d squared is equal to 0. So we actually get a chain complex with d squared equal to 0, and the resulting homology I'm going to call KH. And it's going to be associated to the actual link itself. It's an invariant under changes in the diagram, but we honestly compute it from a diagram. And it's just the homology of the chain complex we drew on the right. Okay, so I've told you about one grading. This is the homological grading. If we go back to the previous page, you'll see that I've drawn these generators of the F2 vector space in a very specific way. And this is because we can really think of this algebra as being graded in a certain way, where X in my conventions has grading -2. So this is separate from the homological grading. It's an internal, what's called a quantum grading. And in my conventions, 1 has quantum grading 0, X has quantum grading -2. So every time I have a generator that has an X in it, it drops down in its internal grading. So that's why these two are in the same quantum grading. And then these are all in the same quantum grading as well. We can carefully define all of these gradings to be absolute. We have to take into account all of the different ways the diagram can be drawn, but just remember that we have two gradings, homological and quantum, and the quantum is actually what allows us to extract the Jones polynomial from Havana homology. Okay, so I'll just add that note up here. Havana homology is ZO plus Z graded. You have the homological grading and you have this extra quantum grading. So now that you have my notation, let me tell you about one of the most important advances in Havana homology, which is Rasmussen's S invariant. Again, just for today, I'm going to work over F2. But let me first tell you about the people involved. So first, this really goes back to the work of Eun-Soo Lee, who developed a spectral sequence and talks about the perturbation of Havana homology I'm about to show you. And then Rasmussen used Lee's work and played with the algebra and got a numerical invariant for knots in S3 called the S invariant. And it's very powerful. For example, one of the big applications that he uses in his paper is that he was able to prove Milner's conjecture. Of course, there are many of them. I'm talking about the one about the genus of a torus knot inside S3. Basically, a torus knot is a very simple type of algebraic, or you could even say it comes from like complex geometry. Or if you see it as a braid, you can immediately see the surface that it bounds, and it has a certain genus related to the genus of algebraic curves. Now the question was, can you actually reduce that genus? Can you find a smaller genus surface in S3 that has that torus knot as its boundary? And it turns out you can't. This was proven previously by Kronheim and Ruvka using gauge theory, but Rasmussen was able to use Havana homology, which to people like me definitely seems easier. So that was very exciting. Since then, I should also point out that Lisa Piccirillo used the S invariant to prove that the Conway knot is not sliced. So that was also extremely exciting and much more recent as well. Okay, but I'd be lying if I said I actually were using Lie homology here. I'm actually using Barnaton homology. And that's because Lie homology doesn't quite work out as an invariant if you are working over characteristic 2. And since I'm being lazy with signs, especially during talks, I'm using Barnaton's version of this sort of idea. It's algebraically very, very similar. It's just that we're in a characteristic that doesn't work for Lie homology. Okay. So now think back to the first thing I talked about in the warm-up. I said that Havana homology is basically using this TQFT associated to the Frobenius algebra that was just F2 adjoint X mod X squared. Now I'm going to make a modification. My ground ring is now going to be F2 adjoined some indeterminate, just a variable called H. And specifically, H has quantum grading -2, just like X. Let's define a new Frobenius algebra. I'm going to take my ground ring, which remember has H in it. Again, take the polynomial ring, but now I'm going to mod out by the ideal X squared is equal to HX. So if you want to be more careful, maybe write X squared minus HX. But the point here is that whenever I see an X squared, I know I can replace it with an HX. So it helps me. Notice that this is a graded relation because X and H both have quantum grading -2. That means that I'm setting two things that have the same grading equal to each other. So I haven't destroyed the grading on my Frobenius algebra. Okay, so now my chain complex, I'm going to call it CKH graded Barnaton. This is because you might also see filtered versions of this, and there is a way to translate between them. But for the purposes of what I'm going to talk about later, I want to really focus on a graded version of this theory. So let's just take a moment to look at the multiplication map to see what has changed. Okay, so in this algebra, again, I have the same basis elements. But now if I multiply x and x, well, I get h times x. So here's one way to write it down. You could say 1 times 1 is 1, x times 1 times x is x, and then x times x is going to be x with a coefficient of h. This is a very common way to look at it. But I actually want to think of everything as an F2 vector space, even though now I have this extra variable h. So I actually want to think about the fact that there are actually z plus copies of each of these generators corresponding to each power of h that you can multiply it with. So the picture I'm going to use to make this look clearly graded is that x tensor x is going to be mapped to this other generator that is equal to h times x. And notice that because h has grading -2, it's actually exactly 2 lower in quantum grading than x. So now you see that my differentials are still preserving the grading on my individual generators, my homogeneous generators. So this is a graded theory. And so the homology is also graded. Now here's the interesting fact. I should probably add a diagram there. This complex has a very interesting structure. If you take the homology and you mod out by the torsion submodule, it turns out that the free part is just going to be 2 copies of your ground ring. So a lot of the people who come from a not Floer world would say that you have 2 infinite towers. And this is because I can draw the following cartoon. Let me move my multiplication map a bit up here. So the following is just a cartoon because the torsion module is very much canonical, but it's not like a direct summand with the free part. So this is going to be slightly weird. Maybe if you chose a really nice basis, it would work out. So what I see is that the complex that comes from Kovanov homology, or technically Barnaton homology here, is going to have these 2 infinite towers such that each of these dots that are on the same vertical line are just h shifts of each other. And then elsewhere, right, there's torsion, which means that these are not infinite towers because once you multiply by h too many times, it turns out there's only h torsion because we're working over this PID. You leave just the existence of anything, it just becomes 0. So it's killed by h. And here is what Rasmussen's S invariant is. Rasmussen showed in the context of Lie homology, and this is also true when we work with Barnaton homology here, you're going to end up with tops of the towers that are precisely 2 quantum gratings away from each other if you choose your gratings correctly. So this is going to be a cartoon. But if you can get the picture to look like this, you take the average, and this quantum grating is going to be your S invariant. So the S invariant is basically measuring how tall your infinite towers are, or where the tops are. So one way to define this, that's probably a little bit more precise than my cartoon, is to say that the S invariant associated to a knot in S3 is, well, you take the maximum quantum grading of a homology class eta such that eta is non-torsion, and then you subtract 1. So now I don't care about my towers being all precisely whatever height, but certainly there is a maximum height here, and I just subtract 1. Okay, so now that we have this cartoon in our heads, I'm going to switch over to knot Floer homology to give you a sense of what algebraic structure knot Floer homology has, what things we can do with it, and then we'll bring it back to Hovanov homology to see what we can do with U1 cross U1 equivariant Hovanov homology. Okay, I'm going to check the time. Okay. So I think that somehow the background on Floer homology, actually understanding the fundamentals of it goes into a lot of, you have to understand the analysis of it, but they are very, very computable. So I'm actually going to just describe knot Floer homology via an example. So I should point out here that the relevant people are, well, Heegaard-Floer homology was introduced by Oshvath and Szabo. And then knot Floer homology was introduced by Oshvath and Szabo and Rasmussen independently. So let me write down their names. And then I will also talk about, oops, wrong color, the numerical invariant that I talked a bit about when we were on the title page, called upsilon. And this was introduced by Oshvath, Lipschitz, and Szabo. So once again, I'm going to let my knot be inside S3 for the purposes of this talk. And the key thing to note here is that the Heegaard-Floer homology of S3 is one-dimensional. And I won't say if it's hat or whatever, but the point is that it's a very, very simple object from the point of view of Heegaard-Floer homology. Now, knot Floer homology is actually going to be a filtration on the complex that you get from looking at a diagram of S3, because we are looking at basically the complement of a knot in S3. And so somehow, like, you can write down this complex whose total homology is very, very simple. But if you think about the actual extra information coming from your filtration, then you get the information of the knot. And this is sort of analogous to the fact that we had the fact before that if you take the total homology of a certain version of the complex I looked at before, basically I'm going to think about, let's say, localizing at H in the previous algebraic structure. Then you get to something very simple, which is that you just have two bi-infinite towers. Alternatively, if you were thinking about working with the filtered theory, it would be even more similar to this picture. Okay, but enough about that. Let's just start computing. I think I would like to do the trefoil because, again, it doesn't have a lot of crossings. Specifically, I'm going to do the left-handed trefoil because that's just what it ended up being after I drew the picture. So I have to start off with a nice diagram, and I'm going to draw a very oddly shaped torus. It's an uncomfortably proportioned torus, but I'm still going to make it smile, so it's okay. So this is my torus. And Hilbert-Floer homology is really a Lagrangian-Floer intersection theory. So that basically means you have some symplectic manifold, in our case, this two-dimensional surface called the torus, right? Already symplectic. And then we have two Lagrangians inside, and well, curves are half-dimensional on a two-dimensional space. So here we go. Here's my first one. And you should also imagine that it goes in the back, but I'm not going to draw it so things don't get too busy. This is going to be our alpha curve, and then here's our beta curve. And now I'm going to sort of shift away from the standard notation in Hilbert-Floer papers, just for this talk. There's going to be a special point here called U and a special point here called V. And the idea is, this is exactly going to describe a left-handed trefoil. So I will doodle something over here and I'll erase it later. Okay, so I look at my weirdly shaped donut, and if I think about a particular knot, okay, so this is embedded in S3. Let's say I come out of U, and you can think of the knot as basically like some kind of primordial dragon that is traveling through the earth back when we just had so much lava flowing around and we had some water. The way that I think about it is the earth is completely covered in water, but then there's magma underneath. And somehow this dragon is able to swim in both regions. So above the crust of the earth, the dragon is allowed to travel anywhere as long as it doesn't go through any of the blue walls, which are ocean walls. And then underneath the crust of the earth, there's going to be a giant wall inside the magma that it can't pass through. So let's say that the dragon first comes out of U. Well, okay, so it's coming out of here. It needs to somehow get to V without passing through the blue wall. And I believe the way to do that is to go around the back. So I want to go like this, and then I want to go through the hole, through the donut hole. And now I've sort of landed myself inside the blue curve, so it's safe to just go like this. Okay, but now it's going through the crust of the earth, and now it's going to be not allowed to cross any of the red walls. So it needs to get from V to U without passing this line, or this circle that also exists in the back. Now to do this, remember that we're under the crust. So when I think about this crossing here, secretly there is a height difference, because over here the dragon was swimming in water. Over here the dragon is swimming in magma, which is underwater. So I have to do an undercrossing. And then I think I'm going to just swing around as you would expect. Okay, so swinging around. And again, because this was when the dragon was in the water, which is above the magma, this next crossing that I make is also going to be, I'm going under here. Okay, and then now if you actually squint a bit or ignore the rest of the diagram and look at the drawing that I just drew in black, you'll realize that this is actually the left-handed trefoil, which for reference should look kind of like this in this picture. So that's how we basically look at this picture and know that we're talking about the left-handed trefoil. So we essentially ignore this drawing of the knot and we just work with these this picture. Okay. So let me shrink this so that everything else will fit. Knot-Fuller homology is also a, you compute a chain complex first. It's a homology theory. So I'm going to describe for you the chain complex. Let's start off with the chains. Well, I look at this picture on the left here, and I see three intersection points. There's A, B, and C. And again, I want to move toward the algebraic structure that I care about later. So I'm actually going to look at, let's see, you really want to look at F2 generated by A, B, and C, but I want to work with this ring that has a U and a V in it, and these are just variables, just like we had H in the previous Barnaton picture. Okay, so in other words, this is a very convoluted way of writing this, but you just have all the U and V multiples of A, B, and C. So U to the 6th power, V to the 5th power times A is a homogeneous generator in this case. The differentials are going to be very interesting. They're going to count these disk regions that look like the following. So if I have X down here and Y up here, and as I go around a disk connecting them, I see red first, and then I see blue. That means that I have Y is a component of the differential on X. So in very loose terms here, I'm going to say Y is an element of the differential on X. And then I'm going to quickly erase it because we're not really talking about sets here. It's just a summand. This is going to represent basically one of my arrows in the dots and arrows pictures. But let's actually write down the differential because this example is so small. First of all, I see a disk here from A to V because it's red and then blue. But because this disk is going over my special point U, I'm actually going to say that I'm multiplying the target by U. This is sort of moving away from perhaps how Oshvat and Szabo wrote this theory down, but it's going to work a lot better with my Barnaton picture from previously. So basically, A maps to U times V, because I pass over U and I get to B. Similarly, there's a disk from C to B, but that goes over V. So I'm actually going to say that C maps to V times B. And you can check that there are no other disks in this picture. So this is the full differential. But of course, my chains have all of these multiples. So I really mean like you have to multiply both sides of these arrows by any monomial, and that is also going to be part of the differential. We can draw a visual picture of what's going on here. And let's say that we're in some sort of plane that looks like this. I'm going to define GRV as the V power of whatever I'm looking at, and GRU as the U power. So for instance, U times B is going to be located somewhere over here. Okay, so without reference to wherever the axes are, you'll see this familiar picture. So there's going to be some edge defects when the monomial coefficients of my generators are very low. But certainly when I get to V times A, that gets mapped to UV times B. And U times C gets also mapped to UV times B. And you can notice that I can take this picture and multiply by any monomial U to the M, V to the N, and I will still see a little bit of the chain complex that looks like this, and they're just sort of shifted whichever direction you want. But as I move the other way, well, there are some problems because, for instance, if B were over here, nothing is going to map to it because there is no V inverse times A in my complex. So that's sort of the reason why you should think that we have some infinite pieces and then we have some torsion pieces. Okay. So now if you want to see the homology of S3 here, notice that this actually is one-dimensional, or rank 1 if I'm working over some much bigger ring. But interestingly, you can also think about filtering this complex. And I'm going to go on to the next slide to kind of zoom into this picture a bit more. So here's what upsilon would look like. I see a bunch of pictures like this. And upsilon is going to only care about the non-torsion pieces. So all of that edge defect business I was talking about won't matter. Stuff like this. If you look at any slope of lines starting from flat, like this, you can move this up and down. So I'm looking at my differentials and they have to sort of map into smaller pieces of my filtration. Let me actually start off with an analogy I always like to talk about. You should really think of a filtration on a complex as basically, let's say your complex is made up of generators, which are these dots, and arrows, which point from one dot to another dot. You put all your dots in this onion, and the onion layers sort of represent like a grading of sorts. But a filtration is saying that chains don't have to belong in a particular grading because you don't have a graded complex necessarily. Your differentials might move between the layers. So you should always think that a filtration level is whatever remains of your onion as you peel back the layers. So what's going on with the filtration is that my arrows are always going to be pointing towards the center of my onion, so that when I peel off any number of layers of my onions and I just end up with something smaller, I still have a subcomplex. It's still a chain complex. So when I look at this particular example, I have an onion that maybe looks like this, right? But it's so big that I'm effectively seeing straight lines, and that's why I was drawing the straight line. So if I'm filtering this way, so that up here is inside the onion, out here is outside the onion, when I get to this point, this generator has left my smaller onion. It's no longer there. This becomes acyclic. And now the homology is nothing. So what I end up doing as I draw this horizontal line moving up and down is I can basically measure at what point I stop getting any homology. And that is basically going to tell me the definition, the value of upsilon. So remember that I said upsilon was actually a function of t, where t is between 0 and 2. Well, t is going to tell me the slope of what I'm going to say the boundary of the filtration levels. So for instance, for a different t, let's say t equals 1, I know that that is going to be diagonal lines of slope -1. I didn't tell you the actual formula, but that's what it's going to be. And here, I basically see that I can move, and then once I pass this point, I have just, I guess, a single homology inside my smaller onion, and then it leaves. So by tilting the line all the way from vertical through negative slopes to 0, I will be able to, for each t, come up with a numerical value that becomes upsilon. Okay, so now with that rough picture in our minds, I'm going to talk about back to the Fibonacci homology. And here I will actually give you the definitions. So let's first start with U1 cross U1 equivariant Fibonacci homology. In case you're wondering about the name, you should think of, if you're familiar with it, this is as opposed to U2 equivariant quantum homology, which is universal quantum homology. And that's where you have a variable h and t, and your Frobenius algebra mods out by just the most general quadratic, x squared minus hx minus t. Here, we are going to further break that down and actually say, what if the roots of your quadratic are in my ground ring? And this was introduced by Khovanov and Robert. And I also want to point out that it was also studied very extensively by Taketo Sano, who wrote a very interesting paper about a lot of stuff related to our work. So here's my new Frobenius algebra. The ground ring will now have the same variables as in the Hager-Floer, the not-floor picture. My Frobenius algebra is my ground ring, again, the polynomial ring, and we're modding out by x minus u times x minus v. So it's still commutative, but somehow we are not working with a very nice integer domain or anything right now. This definitely has some interesting properties, but it's okay. All the important properties are still there for us to think about the topological applications. I am again going to write down the notation for the chain complex, and for the reason that this paper by Khovanov and Robert uses alpha 1 and alpha 2 here. So I'm going to actually use alpha as my subscript to denote this version of Khovanov homology. So as it stands, if you think about u and v as having grading -2, just like h did before, this is actually a graded theory. So I want to point out here that this version is a graded homology theory. And again, we can check. So let's look at the multiplication map. Okay, 1 times 1. This is the last time I'm writing this. Oops. 1 tensor x, x tensor x. But secretly, it's these 4 things times all of the monomials u to the n, v to the n. We still have 1 times 1 is 1, and so on. But now x times x, if you multiply this out, has sort of like 3 arrows coming out of it. However you put it, you can say that there's a u times x, there's a v times x, but then there's also this other summand, uv times 1. So it's u times v times 1. So we go down -4 in quantum grading. Okay, so this is still a graded theory, but now I'm going to do something similar to, I guess, the upsilon story, which is that I'm going to define what's called a T modification. You don't really need to remember that term. All I'm saying is that for each T inside 0 to 2, I'm going to come up with a filtered version of this complex. What I'm going to do is basically mess with the grading of this guy right here. So I'm going to say that u and v are going to pick up, we're going to define a new grading called GRT that isn't going to keep u and v at grading -2. That's going to depend on t. Specifically, the formula is GRT of a previously homogeneous thing, a quantumly homogeneous thing. Looks like this. We're going to basically ignore the fact that u and v are there and just take the quantum grading of G. Now G here, I should specify, is just a homogeneous generator of just the simplest version of Khovanov homology. kind of like the intersection points in not-Floer homology. But then I'm going to subtract t times the number of copies of u. So this is like the GRU. And subtract 2 minus t times the number of copies of v. So now I've basically replaced the internal quantum grading with this weird internal grading called GRT. And whenever t is between 0 and 2, it turns out that this is still a filtration on this complex. So if I just take these chains and I think about the differential, but I give them a different grading, it's no longer a graded complex, but it is a filtered complex in the sense that I can put it in this onion and all of my differentials point either within the same onion layer or into the onion. Okay, so I can describe this. It might just help for anyone taking notes or anything. This is CKH alpha T modified of a diagram. And you have to basically just remember the data of what are the differentials in this U1 cross U1 equivariant homology, and also what is the grading. For the experts out there, if you look at Khovanov's papers and also Khovanov-Robert, this is because these two represent the U1 cross U1 equivariant cohomology of a point and of S2. But I have no more to say about that. It's very profound, but for our purposes, this is all it means. So now let's think about what we can do with this. I can't draw an example for you like the Trefoil and not-Floer homology because, as you know, the Khovanov complex is going to get very, very big. Just for every crossing that we have, we sort of double the size of our complex. But I can tell you that you're going to look at a picture that looks like perhaps something like this. So let's say you have some point here. It could have differentials that increase your U power. So again, secretly, I'm thinking there's this GRV and this is GRU, and I'm on this plane, keeping track of the copies of U's and V's. So we saw that the merge map had something that was U times X and then something that was V times X. You could also have something that just preserves the U and V gradings. This is just a regular Khovanov differential. And then you could also have this thing that moves diagonally. So this is like multiplying by UV. But now you can do the same sort of trick as with the Trefoil and not-Floer homology. If I take any line of slope, either negative infinity and then all the way up to 0, anywhere in there, then I can filter this complex. And then I also still have the fact that GRT of my, let's say, diagram, the maximum GRT grading of a homology class such that the homology class is non-torsion -1 is still well defined. So remember, this was how I defined Rasmussen's S invariant. And it really comes down to the fact that if I localize by a very particular element, it turns out it's actually V minus U in our case, the torsion is very well controlled. So we only have V minus U torsion in this complex, even though we don't have a PID. It's sort of weird situation. But we still have basically what you could consider as 2 infinite towers, although maybe the dimension of the towers is sort of weirder in our case. So you can define this and you can subtract 1. And this is because you have these two things and you want to sort of deal with some quantum grading considerations. And this is what we're basically defining as, oops, sorry. This is without the 1. ST is going to be GRT of D minus 1. Maybe I should have just written that in one line. Anyways, this is a number now for each value of T. So let's think about some properties of this. First of all, you notice that within our construction, U and V are entirely symmetric, because let's say at T equals 1/2, well, if I want to look at what happens when T is equal to 1.5, all I have to do is switch the roles of U and V. So we know that this function is going to be symmetric about T equals 1. You can also check that because of the way that we define this filtration, this is a concordance invariant. And concordance just means, if you think about knots in S3, you just have a set of knots. There are some relationships between them, but if you think about knots in S3 on the boundary of B4, and you mod out by this relationship called concordance, which is basically saying that you can build a cylinder between two knots if you allow the fourth dimension. So that collapses the equivalence classes of isotopy classes of knots. Then you actually get knots are a group. So that is just absolutely wonderful, which is why we care about understanding which knots are equivalent to others once we allow the fourth dimension. So this is saying that if you have a concordance between two knots, they have the same S of T. And then there are also other things, such as if you really think about this complex, at T equals 0 and T equals 2, it's really constructed from a bunch of copies of Barnaton's complex. We have two indeterminates here. There's the V's and the U's. But if you slice it just right and you look at the associated graded object with respect to the filtration GR0 or GR2, you'll just basically get a bunch of copies of Barnaton's complex. What else should I say? Give me 1 second. Okay. The last thing I want to point out about this is that there are a lot of questions that are still unanswered. So first of all, I don't actually know if this is a homomorphism from the concordance group to piecewise linear functions from 0 to 2. And I ask this because S is a homomorphism and upsilon is also a homomorphism. I want to point out the work of Ballinger. Oops, sorry, writing too small. Who developed another upsilon type invariant called phi, which is a homomorphism. This sort of doesn't have the symmetry between U and V just from this version of Concordance homology, but it uses, his work uses the E-1 differential from this other spectral sequence that's related to Concordance homology by work of Rasmussen. And by blending the quantum filtration on Lie homology and also this other filtration, you get another upsilon-like invariant, which has a lot of the same properties as upsilon. I also want to ask about what other constructions from knot-Floer homology can we also apply here? So for instance, knot-Floer homology is very much related to the Hager-Floer homology of not just S3, but also other 3 manifolds. So if you do surgery on a knot, there's a way to sort of read off information about the resulting 3 manifold from your knot-Floer complex. Now in Concordance homology, we don't actually have Concordance homology for just inside arbitrary manifolds. somehow I do think of Lie homology as an invariant of S3. Like you always see these two towers, no matter what knot you work with. But you could think about it from the algebraic point of view and say, if I do the same calculations and constructions on this UV version of Hovanov homology, well, do I get an invariant of something? What does that represent? So the question is, if I do the same algebraic construction, what information am I getting? And I don't know. I guess, oh yeah, and the third thing I want to say, maybe I'll just say this out loud, is there's also the annular Rasmussen invariance introduced by Grigsby, Licata, and Verley. And what's interesting about this invariant is it's an annular invariant, so it's not for knots in S3. But because annular Hovanov homology is so related to, braids and braid closures, and then braid closures in turn are very much related to contact geometry and transverse knots, they were able to ask some questions about certain conjectures you can make using this invariant. So the question here is, with this version of a complex to play with for knots in S3, what kinds of conjectures can you make? So with that, I'll stop here, and I want to thank you for joining. So I'm going to write a thank you slide. And if you have any questions, you can always email me. I am melissa-zhang.com, and you can find all my information there. Thanks for watching, and I hope to see you around in person sometime. Have a great day.